Okay, let's unpack this. Quantum computing, you hear about it everywhere, right? Incredible promise.
Absolutely. Solving problems classical computers just can't touch.
But, and it's a big but, there's this huge bottleneck.
Yeah.
Designing the software.
hmm
It's incredibly tough. You need to understand, well, deep quantum mechanics and the nitty-gritty of the physical hardware. It's a massive barrier for developers.
It really is. But what's fascinating, I think, is how the industry is starting to, tackle that head on.
How so?
Well, imagine you could design the quantum software without needing the actual physical quantum computer right away
Okay.
by simulating its hardware in a controlled digital space. Think of it like a shortcut.
A virtual quantum environment.
Exactly that. It's a powerful new paradigm.
Right. And that's what we're diving into today, this whole comprehensive blueprint approach.
Using virtual quantic blueprints.
Precisely. Designing quantum software through virtual hardware. We'll look at how these blueprints let you manipulate things stage by stage.
Offering a really visual, kind of intuitive way to build this stuff.
Yeah, you're in for some real insights, I think, because this is where it gets genuinely interesting.
It really does.
So, okay, at the heart of this virtual quantum environment is this thing called a virtual quantic blueprint. What exactly is that?
Right. Think of it as like a dynamic digital map of the quantum hardware.
A map.
Yeah, it's the foundation. This blueprint, it specifies everything, the properties, the states, the operations of your virtual qubits.
For what they are.
Exactly. Their very nature, their ontology, things like superposition, entanglement, but then it also maps their structural relationships.
That's how they're connected.
Yeah, connectivity, interaction pathways,
Yeah.
all within that simulated quantum circuit, their topology.
Ah, okay. So it's much more than just a drawing. It's like a living model of the quantum system.
Precisely. It's adaptable.
So what are the key building blocks, the main components inside this blueprint?
Fundamentally, you're working with three core things. First, the virtual qubits.
The digital entities.
Right. And you can configure their states 0, 1, or, those quantum superpositions.
Okay.
Second, you've got the states themselves. These are the mathematical descriptions, like vectors, showing all the possibilities for the qubits.
Got it. And third,
Operations. These are your quantum gates, the tools you use, and also measurements, things that actually change or observe the qubit states.
so the blueprint acts like this flexible template, letting you manipulate the system step by step, but keeping its core nature intact. Sounds like a really powerful tool for complex design work.
It absolutely is. And the manipulation, it happens in these distinct stages.
Stages.
Yeah. Each stage has its own specific blueprint detailing the configurations and operations for that step. It mirrors the whole life cycle of a quantum computation.
Okay, like from start to finish.
Exactly. From preparation through execution right up to getting the results out.
Let's walk through them then. Stage 1, initialization.
Correct. Here, the blueprint just sets the starting conditions for your qubits.
Like setting everything to 0.
Yeah, could be all zeros. Or maybe you use a Hadamard gate right away to put them into superposition. Yeah. The configuration defines how many qubits, their initial states, maybe some early entanglement.
To ensure a consistent start.
Exactly. A predictable starting point. For instance, a blueprint might set up 3 qubits in what's called a GHZ state. That's a highly entangled state ready for some multi-qubit experiment.
Okay, makes sense. Then you move into the actual doing part, stage 2.
Yeah.
Applying quantum gates.
Right. This stage is where you lay out the sequence of gates.
Like Hadamard, CNOT.
Yeah, those kinds of things. Poly-X gates, too. You specify which gates hit which qubits and when.
And these gates manipulate the states.
They do. They create the superpositions, the entanglement, the phase shifts, all the stuff that makes quantum algorithms work.
So the blueprint needs to be precise here.
Oh, absolutely. Gate parameters, target qubits, it's all detailed for really fine control over how the quantum state evolves over time. A classic example blueprint might say, apply a Hadamard to qubit 1, then a CNOT linking qubit 1 and qubit 2. That creates entanglement, a Bell state.
Right. So once you've done your operations, you need to get the answer out. Stage 3, measurement.
Exactly. This blueprint details when and how you measure the qubits.
Which collapses their state.
Right. Collapses them down into classical bits, zeros and ones that we can actually use.
And the blueprint defines how.
Yeah. How the outcomes are recorded, how they're analyzed. You often visualize these as probability distributions. This step basically finalizes the computation.
It's how you extract the results.
So, for example, if you measure qubit 1 after it was entangled with qubit 2, you'd expect to see correlated outcomes. It reflects their shared quantum history.
Gotcha. So that's how you pull answers from the quantum realm. And then there's a stage 4, advanced manipulations.
Yeah, this covers the more complex stuff.
Okay.
Things like creating entanglement across many qubits, implementing error correction codes, which are super important, or maybe dynamic gate sequences that change as the computation runs. Examples could be building cluster states, which are resources for certain quantum computing models, or running a quantum Fourier transform. It just extends the system's capabilities for really sophisticated algorithms.
And you mentioned these blueprints are sort of grid-like.
Often, yeah. You can think of it like a grid where the cells are qubits and their states, and they're connected by the operations that dictate how the whole system evolves topologically.
This all sounds incredibly powerful, this virtual approach. But why is it so crucial right now? What's the big problem it's solving in the real world of quantum development?
That's a key question. It directly addresses what people call the hardware gap.
The hardware gap?
Yeah. I mean, developing quantum computing is just inherently difficult. You've got the weirdness of quantum mechanics itself, plus the incredible complexity of building the actual physical hardware.
Right.
We're currently in this phase called the NISQ era, noisy intermediate scale quantum. Yeah, current devices, they're really limited. They're susceptible to noise from the environment, internal noise, and often the qubits don't have great connectivity between them. So even if you have a machine with lots of qubits, many of them might just be dedicated to trying to correct errors, leaving only a few for the actual calculation.
So it's not just building them, it's making them work reliably, dealing with all those imperfections.
Precisely. Decoherence is a huge one.
That's where they lose their quantumness.
Essentially, yeah. Qubits lose their delicate quantum features, coherence, entanglement, because they interact with their surroundings. It introduces errors, undermines the whole point.
So making them last longer is key.
Huge priority, sometimes called Schoolcop's law, this idea that coherence times are improving exponentially. There have been advances like using 3D cavities instead of flat ones for superconducting qubits. That helps shield them a bit better, extends coherence times.
And all this uncertainty around getting truly fault-tolerant machines, that makes companies hesitate on the software side.
Understandably, yeah. Why invest millions developing software for today's quirky hardware if it might be obsolete tomorrow when a different, better technology comes along?
Right. Risk.
Exactly. And that's where these virtual quantum processors, VQPUs, and simulators really shine.
They bridge the gap.
They do. They offer a feasible, cost-effective way to get started. Developers can run quantum programs in a high-performance computing environment
let's unpack this.
Tied to
Quantum
one
computing,
specific piece
you hear
of
about
hardware.
it everywhere.
Hardware
right?
agnostic.
Incredible promise.
These virtual
Absolutely.
processors,
Solving problems
they
classical
emulate a
computers
kind
just
of
can't
generic
touch.
quantum
But,
machine.
and it's a
A
big
logical version
there's
of
this
what
huge
future
bottleneck.
hardware might look
Designing
like. It's a crucial
the
training
software.
ground.
It really sounds like
It's
a way to
incredibly
sort of
tough.
You
Jumpstart
need to
the
understand
software side of
well,
things even while the
deep
hardware catches
quantum
up.
mechanics.
Are
companies
and
actually
the
doing this
nitty-gritty
now?
of
Oh,
the physical
absolutely.
hardware.
Real-world
It's a
examples
massive
exist.
barrier
Daimler
for
Truck
developers.
AG,
It
for
really
instance.
is. The truck
But
company.
what's
Yeah.
fascinating, I think, they're
is
looking
how
into
the
quantum's
industry is
potential
starting
for
to,
simulating
tackle
materials,
that head-on.
science for
How
better
so?
batteries.
Well,
cell
imagine you could
simulation,
design the
understanding
quantum software
battery aging,
without needing
even
the
things like
actual
boosting AI or
physical
managing
quantum computer
autonomous
right away.
vehicle traffic
By
flow.
simulating its
Volkswagen AG is another
in a
one.
controlled
They're exploring
digital
quantum
space.
for
Think of it like a
optimization
shortcut.
A
problems.
virtual
And
quantum
they emphasize
environment.
it's not
Exactly
just
that.
about
It's a
speed,
powerful
it's about
new
tackling
paradigm.
fundamentally different
And that's what
kinds
we're
of
diving
problems.
into So today, this this virtual whole blueprint approach
Yeah.
lets them design for the
Using
future
virtual
today.
quantic
That's
blueprints.
the idea.
Precisely.
Anticipate
Designing
and prepare.
quantum software through
You mentioned
virtual
visualization
hardware.
being key.
Well, look at how these
does
blueprints
seeing
let
these
you manipulate
blueprints
things stage
actually
by
help
stage.
designers
Offering a really visual
grapple
kind of
with these really
intuitive way
abstract
to build
quantum
this
ideas.
stuff. Visualization
You're in for
is
some real
just
insights, I think, because this is where it
crucial
gets
for human
genuinely
intuition,
interesting.
definitely.
It really does.
And also
So,
for the
okay,
virtual systems
At the heart
themselves
of
to kind of
this
understand
virtual
what's going
quantum
on.
environment
What kinds of visualization?
is this thing called
Well,
a virtual
for single
quantic
qubits, you have the
blueprint.
block sphere. It's
What
a great way
exactly
to
is that?
picture its
Right.
state superposition
Think of it as
phase, all on a
like
sphere.
a dynamic
for multiple
digital map
qubits, which
of
gets
the quantum
complicated
hardware.
fast. You
A
use
map.
things like
Yeah,
state
it's the
vectors or
foundation.
density
This
matrices.
blueprint,
These
it
can also be
specifies
visualized, though it's
everything,
more
the
abstract.
properties,
And the
the
operations,
states,
the
the
gates.
operations
Circuit
of your
diagrams,
virtual
those are
qubits.
fundamental.
For
You
what
see
they are.
lines for qubits,
Exactly. Their
boxes
very
for
nature,
gates. It
their
gives you that
ontology,
topological view, the
things like
flow of the
superposition
computation.
entanglement,
And
but
really
then it
importantly,
also maps
modern
their
tools
structural
are
relationships.
interactive.
How they're connected.
Real-time
Yeah, connectivity,
simulators
interaction
let you tweak
pathways,
parameters
all within
change
that
a gate,
simulated
adjust a
quantum
qubit
circuit,
state, their topology,
and see the effects
Ah,
immediately.
Okay. So it's
At
much more
immediate
than just a
feedback
drawing.
must
It's
be
like a
powerful.
living model of the
Immensely.
quantum
It
system.
helps build that
Precisely. It's
intuition.
adaptable.
Now,
So
speaking
what are
of
the
making
key
the
building
abstract
blocks, the main
tangible, I know there's some
components
really
inside this
fascinating
blueprint?
work out there.
Fundamentally,
like
you're
the
working
AI
with
IOA
core
Genesis
things.
Engine
First,
project.
the
They talk
virtual
about things
qubits.
like
The digital
cosmic
entities.
visualization.
Right. And you
Does
can
that kind of
configure their
advanced
states
thinking
0, 1,
connect
or,
to
those
these quantum blueprints?
superpositions.
It's an interesting connection.
What
Second,
the Genesis
you've got the
Engine
states
project
themselves.
explores
These
is
are the
creating
mathematical
really
descriptions,
compelling
like
visual
vectors,
narratives
showing all the
Narratives.
possibilities for the
ways
qubits.
to depict the
And
internal
third,
processes, the symbolic
operations.
transformations happening
These are
within
your
a
quantum
complex
gates,
system.
the tools you use,
Taking
and also
abstract
measurements.
code or data and
Things
letting
that
it
actually
resolve into
change or
symbols you can
observe the
actually
qubit states.
recognize and
So
understand.
the blueprint acts
That's where
like
you
this
hear
flexible
ideas like
template,
crystallographic
letting you manipulate the
glyphs.
system step by step,
Glyphs.
but keeping
Sounds
its
complex.
core
It
nature
is,
intact.
but the idea is to
Sounds like
take
a really
abstract
powerful tool
mathematical
for
symmetries, like
complex
the ones
design
that
work.
define
It
crystal
absolutely
structures
is, and the
there,
manipulation
are
it happens in these distinct
types called
stages.
space groups.
Stages.
Yeah,
And turn them
each stage
into
has its own
tangible
specific
visual
blueprint
shapes or glyphs.
detailing the configurations
You can
and
generate
operations
these
for that
patterns
step.
by
It
applying
mirrors
the
the
symmetry
whole life
rules
cycle of a
to a
quantum
starting
computation.
Okay,
It
like
makes
from start
incredibly
to finish.
complex
Exactly,
symmetries
from preparation
visually
through
graspable,
execution, right
So you
up
can actually
to
see the symmetry.
getting the results
And
out.
Let's
can
walk through
you
them then.
animate
Stage one,
these
initialization.
blueprints,
Correct.
these structures?
Here, the
as they
blueprint
change.
just sets
Yes,
the starting
absolutely.
conditions.
There
for
are
your qubits.
advanced
Like setting
animation
everything to
strategies
zero.
for that.
Yeah.
You
Could
need
be all
ways
zeros.
to morph
Or
the underlying
maybe use a
structure,
Hadamard
a
gate
lattice
right
and the
away
glyphs
with them in
themselves
superposition.
smoothly.
How do you
The
do that
configuration defines
Techniques like
how many
interpolation,
qubits there are
LRP,
initial
or
states,
SLARAP for
maybe
moving
some
points
early
around, but the
entanglement
key is
to
what's
ensure
called
a consistent
topology
start.
preserving
Exactly.
morphs.
A predictable
meaning the
starting point.
connections stay intact.
For instance,
the lines don't break, the shapes
a
don't suddenly
blueprint
jump.
might set up
even as it
3
morphs
qubits in
between,
what's called a
say,
GHZ
different lattice
state.
types or different
That's a
symbolic
highly
glyphs,
entangled state
the
ready for
animation
some
remains
multi-qubit
coherent, understandable.
experiment.
It lets you
makes sense.
visually follow the
Then you move
system's
into
evolution.
the actual
It really does
doing
sound like a
part,
living
stage
blueprint
2.
then.
Yeah, it
Applying
does.
quantum
And if we
gates.
zoom
Right.
out to the
This
bigger
stage is where you
picture,
lay
this
out the
blueprint
sequence of
thinking
gates.
connects
Like
to a broader
Hadamard,
concept.
CNOT.
Something
Yeah,
called
those
the
kinds of
quantum
things.
linguistic
Poly
operating
X gates,
system,
too,
or
you
QLOS.
specify which
Okay, what's
gates
that?
hit which
It's like a
qubits
meta
and
framework.
when.
And these
Not just
gates
for hardware
manipulate the
simulation,
states.
but for
They
designing
do. They create
entirely
the
new
superpositions,
programming
the entanglement,
environments,
the phase
languages,
shifts,
maybe
all
even
the stuff
AI
that makes
reasoning
quantum
algorithms
algorithms work.
built on
So the
quantum
blueprint needs to
principles.
be
The
precise
blueprint
here.
idea
Oh,
applies
absolutely.
more broadly.
Gate parameters,
Yeah,
target
the core
qubits,
idea
it's
is
all
that the
detailed
blueprint
for
isn't
really
just for the
fine
hardware, it's
control
for the
over how the
entire
quantum state
programmable
evolves over
material
time.
of
A classic
whatever
example
system you're
blueprint
building.
might say,
So for a
apply a
designer or
Hadamard to
developer
qubit 1,
using this,
then a
this
CNOT linking
QLOS
qubit
idea,
1 and qubit 2.
what does it
That
mean
creates
practically?
entanglement,
How do
a
they
Bell
interact
state.
with this
Right.
layered
So once you've
structure?
done your
Well, the
operations, you need to get
QLOS
the answer
introduces
out.
something
Stage
called
3,
degrees of design.
measurement.
Exactly.
Yeah, it's a way
This
of looking
blueprint
at the design
details when
process
and how you
hierarchically,
measure the qubits.
from the most
Which
fundamental
collapses
layer
their
up
state.
to
Right,
the user
collapses them
interface.
down
Okay,
into
break it down.
classical bits.
So degree
zeros
zero
and
is
ones
the
that we can
base
actually
reality,
use.
the physical
blueprint
qubit layer,
defines
the actual
how.
silicon
Yeah,
or whatever
how the
qubits are made
outcomes
of.
are recorded, how they're
Unprogrammed stuff.
analyzed.
Got it. Physical
You often
reality.
visualize
The
these
degree
as
1 is the
probability
virtual lattice
distributions.
layer.
This
Here,
step
you
basically
abstract the physical
finalizes
hardware
the
into a
computation.
configurable
It's how you extract
virtual
the
grid
results.
or
Mhm.
lattice.
So, for example,
This
if you
lets
measure
designers
qubit 1 after it was
dynamically change
entangled
the
with qubit
space-time
2,
fabric,
you'd
basically
expect to see
defining how
correlated
the virtual
outcomes.
qubits
It
are
reflects
arranged
their
and
shared
connected.
quantum history.
Okay,
Gotcha. So that's how
abstracting
you
the
pull
hardware.
answers from the
Degree
quantum
2
realm.
is the glyphic
And then there's a
layer.
stage 4.
This is where you
advanced
define your
manipulations.
high-level
Yeah,
quantum
this covers the more
algorithms.
complex
Using
stuff.
symbolic
Things
glyphs,
like creating
these
entanglement
visual
across
or
many
coded
qubits,
representations,
implementing
that encode
error
the
correction
core
codes,
quantum
which are super
operations.
important, or maybe
This is like
dynamic
writing the
gate
functional
sequences
logic.
that change
Right,
as
the actual
computation
program
runs.
logic. And then you said it
Examples
gets
could be
dynamic.
building
Yes.
cluster states,
Here's where it gets really,
which are
really
resources
interesting.
for certain
Degree
quantum
3,
computing models.
the runtime
or
and
running a
adaptive
quantum
design
Fourier
layer.
transform.
Adaptive.
It just
Yeah,
Yeah, the
extends the
system
system's
itself becomes a
capabilities for really
codesigner.
sophisticated
There might be a
algorithms.
component, say an
And you
engine,
mentioned these
that
blueprints are sort
analyzes
of
performance
grid-like.
during simulation
Often,
or
yeah.
execution.
You can think of it like a
And
grid
suggests
where the
changes.
cells
Exactly.
are qubits.
It might suggest
and their
mapping
states,
qubits
and they're
differently
connected by
or
the
updating
operations
parameters
that
in the
dictate
blueprint,
how
like
the whole
error
system
rates or
evolves
operational
topologically.
costs to better match
This
what's
all
actually
sounds
happening. It's
incredibly
redesigning
powerful,
the physics
this
of its
virtual
own virtual
approach.
world.
But why is
often
it so
using
crucial
AI
right
hints to
now?
guide it.
What's the
Wow.
big problem
So the
it's
blueprint
solving
isn't
in the
fixed.
real
It's
world
alive.
quantum
It
development?
learns. It evolves.
That's a key question.
Precisely.
It
Okay, and the
directly
final
addresses
layer,
what people
degree
call the
4.
hardware gap.
The
hardware
prototype
gap?
and
Yeah.
user interface
I mean, developing
layer.
quantum
This is what the
computing is
human
just
designer sees is
interacts with.
inherently difficult.
screen.
You've got the
imagine
weirdness
a
of quantum
3D
mechanics itself,
visualization
plus
space, like
the
a
incredible
canvas.
complexity of
It
building
renders the
actual
lattice,
physical
the
hardware.
qubits,
We're
nodes,
currently
the
in this phase
connections,
called the
transformations.
NISQ era,
But crucially,
noisy,
it's
intermediate
overlaid with
scale
real-time
quantum
data.
Yeah,
Current
heat maps
devices,
showing
they're
error
really
probabilities,
limited. They're
cost
susceptible to
annotations
noise
on
from the
operations,
environment,
performance
internal
metrics.
noise.
It lets the
and
designer
often the
instantly
qubits
see the
don't have great
consequences of their
connectivity
choices.
between them.
That multi-layered
So even if you
approach,
have a
from
machine
the
with
deep
lots of
structure up to
qubits,
the interface,
many of them might just be
reminds me a bit of the
dedicated to
story of
trying
the
to
Rubik's
correct
Cube.
errors,
Oh, yeah.
leaving only a few
How so?
for the actual
Well,
calculation.
Erno Rubik designed
not
it
just building
originally
them,
to
it's making
solve
them
a
work
structural problem, right? How
reliably,
blocks could move
dealing with all
independently
those
without
imperfections.
the whole thing
Precisely.
falling apart. The puzzle
Decoherence
part,
is
the
a
colors.
huge one.
That's where
That
they
came
lose their
later when you realized
quantumness.
he couldn't easily put
Essentially,
it
yeah.
back together.
Qubits lose
I
their
see the
delicate
analogy.
quantum
It's like with these
features.
virtual
incoherence,
blueprints.
Yeah.
entanglement.
You're first
because they
building the
interact with their
underlying
surroundings. It
mechanism, the
introduces
fundamental
errors,
rules, the structure that's like
undermines the whole
degree
point.
0,
So
1,
making
2.
them last longer is
And then
key.
Huge
through using
priority,
it through the
sometimes
adaptive
called
layer and the
Schoolcraft's
interface,
law, this
you
idea
discover
that
the
coherence
complex
times are
puzzles or
improving
computations you can
exponentially.
actually solve
There have
with
been
it. You're
advances
designing the
like
very
using
fabric of
3D
the computation
cavities
itself.
instead of
That's a
flat
great
ones for
analogy. It
superconducting
captures that
qubits.
sense of
That
designing
helps shield
the
them a
rules
bit
of the
better,
game,
extends
not just
coherence
playing
times.
it.
And
All
what
the
a journey we've
uncertainty
been on,
around getting
starting from
truly
that core
fault-tolerant
problem,
machines.
designing quantum software,
That makes companies
and seeing
hesitate
how these
on the
virtual
software side.
quantic blueprints
Understandable, yeah.
offer this
Why
really
invest millions
powerful,
developing software
intuitive,
for
and
today's quirky
dynamic
hardware
solution.
if it might be
by
obsolete
simulating
tomorrow
the
when a
hardware
different,
and detailing
better
every
single
technology comes
stage
along.
of
Right.
qubit
Risk.
manipulation.
Exactly.
These
And
virtual
that's where these
environments
virtual
let
quantum
developers iterate
processors
really
quickly.
QPUs and
They can explore
simulators
complex
really
quantum
shine.
ideas,
To bridge the
even
gap.
AI
They
interactions
do. They offer
without
a
being
feasible,
blocked by the
cost-effective
cost-effective
way to
of
get
physical
started.
hardware. Developers
Bypassing
can
the
run
MSQ
quantum
era
programs
constraints
in a
effectively.
high
For
software
performance
development,
computing
yes.
environment that's
It allows
not
that
tied
crucial
to
work
one
to proceed.
specific
And it's
piece
just
of
fascinating
hardware.
how
Hardware agnostic.
visualization
Right.
makes the abstract
These virtual
tangible,
processors,
and how
they
AI gets
emulate
woven
a
right
kind
into
of
the design
generic
fabric,
quantum machine,
letting these
a
blueprints learn
logical
and
version
adapt.
of what
This
future
whole
hardware
approach,
might look
thinking
like.
these
It's a
layers,
crucial
these
training
degrees of
ground.
design,
It really
and
sounds
the
like a
physical
way to
qubit
sort
right
of
up to the
jumpstart
UI.
the software side
It
of things,
feels like
even
it's
while the hardware
genuinely
catches up.
redefining
Are
what
companies
we
actually
even
doing this
mean
now?
Oh,
by designing
absolutely.
a
Real-world
computational
examples
system.
exist.
It really
Daimler
does
Truck
push the
AG,
boundaries,
for instance.
and it
leads
truck
to, I
company.
think,
Yeah.
a pretty profound
They're
question.
looking into
As we
quantum's
get better
potential
at
for
engineering these
simulating
complex
materials,
realities,
science for
right
better
down at
batteries,
these
cell
foundational,
simulation,
symbolic,
symbolic
and
and
battery
computational
level,
level,
even things like
using
boosting
these kinds of
AI or
virtual
managing
blueprints.
autonomous
What
vehicle
new
traffic
forms of
flow,
intelligence, or maybe
Volkswagen
even what
AG
new
is another
kinds
one.
of
They're exploring
realities
quantum for
might we
optimization
actually be
problems.
constructing in the
And they
process.
emphasize
Wow.
it's not just about
That
speed,
is a
it's
truly
about tackling
provocative thought to end
fundamentally
on.
different
What are we
kinds of
building
problems.
indeed?
So
Thank
this
you so much
virtual
for
blueprint
this
approach
deep dive
lets
today.
them
My
design for
pleasure.
the
It's
future
fascinating stuff.
today.
It
That's
really
the
is.
idea.
We hope you listening have
Anticipate
had as
and
many
prepare.
insights and
You mentioned
aha moments
visualization
as
being
we did
key. How
exploring
does
the
seeing these
blueprint of
blueprints
quantum software.
actually help designers grapple